Hello everyone. So we're making progress through this example. Step one, we've created our data. We're making synthetic examples here. Step two, we have fixed our function space or our model to be this logistic perceptron. And now here's for step three. We've got to come up with a loss function to score how well a particular function choice from our class of functions does at fitting the examples that we are given. So just to remind us, here again is the logistic function. I'm going to start off by defining a fairly standard loss function, which is called the squared loss. And we'll use this a lot in the course on various things. And so what it is, it's just, okay, given, so I'll say u here, this is, ax plus b, if we're coming in from a one-dimensional example here. So we put that through the logistic function. That gives us our estimate, right? So that's our output estimate. And we subtract it from the actual label, and then we square the result. So if it's exactly on, this will be 0, loss will be 0. If it's a little bit above or a little bit below, squaring it will cause this to be a positive number. So the loss goes up as we get further away from the true value. So just to show you what this looks like, let's actually implement this first. So I'll say squared loss equals lambda. So we're going to take in here a u and a y. And that is going to be equal to the logistic function evaluated at u minus y squared. And of course, I should define all this stuff first. There we go. Okay. All right, so here's what the squared loss looks like. So if y is 0, it looks like this. If your input to the logistic function u is less than 0, then this is pretty small, particularly the further you get away from 0. So remember, everything to the left of 0 was classified as 0. That was everything below 0.5 in the logistic function. Everything to the right is classified as a 1. So if I'm actually a 0 and I go to the right, then I have a bigger loss. Eventually the loss saturates at 1 though. Okay. Now it's the opposite if the output I'm supposed to have is a 1. So in that case, the squared loss is very low if u is greater than 0. Right, because remember, everything where the logistic function is greater than 0.5 is classified as a 1. So if you're greater than 0, the worst you can do is 0.25, because that would be 0.5 minus 1 quantity squared. And then, yeah, so the further you go, the better you are. But if you're less than 0, and you're supposed to be a 1, then the error goes up. Okay. Now, so we could do that, and so now we have a loss function, and what we can do is take the derivative of the loss function with respect to the parameters of the function that we chose, and then try to minimize it. One problem, though, with this particular choice of a loss function is that we have something called vanishing gradients. If we're too far away from 0, either to the right or to the left of either of these, we notice that they get kind of flat. So the derivative is going to be close to 0 by the time we get here. And we're not really going to be sure if we're supposed to move right or left along this. So that's a problem. It's called vanishing gradients. There's another theoretical problem, which is this is not a convex function. And this is something I'll talk a little bit more about in AI. But for now, know that there's a couple theoretical problems with this choice of a loss function, although we will use it in other contexts. But when it comes to this logistic perceptron, there is actually a better choice called the logistic loss. And it's a little bit less intuitive to define than the squared loss, because for the squared loss, hey, it was just the difference between what the output was and what it was supposed to be. With logistic loss, it's a little bit different. It's the negative log of the estimate if the output's supposed to be 1, or the loss is the negative log of 1 minus the estimate if the output's supposed to be 0. Now we can write this a little bit more simply, actually, as the following. So I could say I don't have to write it piecewise if I do this weird little trick where I say, okay, this is going to be, so if y is 1, I'm just going to say, I want to do that negative log there. So I'll say negative log sigma u times y. Or maybe I'll just say negative y times log of sigma u. If it's 0, then I want to ignore this first one. So let's say minus 1 minus y. So if y is 0, I ignore the first one. But then I activate the second one, which is the log of 1 minus sigma u. So you often actually see it written like this. This is a little bit easier to write than a piecewise function. And it's a little bit easier to reason about too. So that's actually how you would define the logistic loss. Let me go ahead and do that. So I'll say logistic loss. I'll do that in code. I'll say that is, okay, again, it's a function that takes 2 parameters. It's the input to the logistic function and then the desired label. And so I'm going to return negative y times log of logistic function evaluated at u minus 1 minus y times the log of 1 minus the logistic function of u. And if I plot that, here's what I see. So it has the same character. So if the output's supposed to be 0, I have a very small loss for anything less than u equals 0, so that's good. So anything that's supposed to be classified as a 0, if the input to logistic function is u, we've got a pretty low loss. If it's supposed to be a 0 though, and the input to the logistic function is greater than 0, then the loss goes up and up and up, and it actually has a slant asymptote at the line y equals u. So unlike the squared loss, it actually doesn't saturate, it keeps going up. So that's one nice thing. And then you see it's the opposite. It's actually reflected about the line x equals 0. If I'm trying to classify an example that is supposed to be a 1, then I have a very low loss if u is greater than 0, but I have a higher loss if u is less than 0. Okay, so let's just take a moment and let the loss sink in, and then I'm going to explain how we actually use the loss to minimize our parameters, or to choose parameters that minimize the loss over all examples.